This video is going to be a demo of the zero-order length transducer experiment for Module 3 of ME and AE 201. We're going to set up the experiment and then talk about the background of it during this video. The experiment involves use of a linear potentiometer, which is going to be calibrated, and the application that we have in mind is a depth measurement for an ice rover for ice rink temperature and depth measurement. The overview of the experiment is shown here. There's a power supply, DC power supply, a linear potentiometer that's connected with a shaft and a spring to this mounted carriage, which has a micrometer used for indexing position. There's also a voltmeter here for measuring output voltage. We're going to be wiring this up and then indexing position, measuring voltage, and fitting a line between the two. This is part of the broader lab on measurement system behavior, where ice testing rover is our goal, and we're using lumped parameter models to characterize the behavior of measurement systems, looking at the relationship between their inputs and their output, and based on initial conditions using differential equations. The zeroth order system is the simplest of all, and so with that system, we don't have any derivative terms. We just have a simple linear relationship between input and output, using the sensitivity K as the slope between the input and output. This is similar to what we've done in the water depth experiment with the moisture sensor using the Arduino. So during the experiment, we'll be referencing this schematic here, which is from chapter 6 of the textbook. Has a power supply, it looks like a battery here, a multimeter, and then a potentiometer, which is a variable resistance component. There's a wiper in the middle that indicates mechanically moving the center of the resistance, the center of the resistor or the potentiometer, which changes the resistance. As we apply a voltage, this voltage divider circuit will give us voltage proportional on the output to length. Okay. We'll be taking data in a notebook and recording that, following along with the procedure that's written. So essentially what the procedure outlines is setting this up and repeating length, indexing, and voltage measurement until we can fit a line to that. So some of the background, the procedure that we're following is part of the assignment 3.1 zero order length transducer static sensitivity outlined here. So as part of the process, you're going to be stepping through each of these things. I'm going to be going over them in more general terms. You'll want to follow step by step and then make sure that you complete each of these items here. The background is in the textbook, chapter 3, where again, we're looking at measurement systems. So I encourage you to read this and then also to check out chapter 6 of the textbook, which shows the relationship between voltage in and out for a potentiometer length transducer here, and also this circuit that we're going to use. There is a chapter 12 mention of displacement sensors more generally. It also includes potentiometers and LVDTs, linear variable differential transformers. I'll touch on that at the end of this discussion. So with that, I'm actually going to stop sharing my screen and then move the camera over to the bench so we can look at the setup here. So on the bench, you can see several components. On the black, we have a Global Specialties DC power supply, 2 multimeters. We really only need 1. We can use either in this lab, a Fluke, the one that's yellow, and a METEX meter that's gray. And then we have our Hamden experimental board here that mounts a micrometer and a potentiometer. Then we have some jumper wires as well. So power supply, Fluke multimeter, METEX multimeter, some jumpers. These jumpers have banana on one end, that's what that's called, and also mini banana on the other end. And then we also have some generic clips-based jumper leads for this setup as well. The potentiometer is this component right here. There's a make, model, serial number information here, as well as the resistance. The potentiometer has 3 different terminals, electrical terminals, the top and bottom, and the middle that corresponds to the wiper. We essentially apply power to the top and the bottom. So generally we'll consider this the ground, and this as the positive, and then we'll measure voltage out of this. Generally we're going to have positive and ground on our voltmeter here. And as we index this up and down using the micrometer, we should see a voltage difference. So set this micrometer spindle down to where it's close to 0 in the beginning of the experiment. So we've got the 0 position set here. With the multimeter, one of the things we can do, if we're using the Fluke multimeter, is we can turn it on and then set it to measure resistance. And measuring resistance, we can take a look with our leads at the resistance of this particular potentiometer. And this one reads 5.389 kilo ohms. Now that's slightly different than the spec on the side, which is 5 kilo ohms. But that's the actual overall resistance. As we index the micrometer, we're going to see that the resistance across the center wiper changes. So currently it's 1.56. If we were to crank this out, we'd see that it changes as well. Okay. So more generally, we're going to have the meter set to voltage for measuring output voltage, or if we use this meter here, Metex meter, we'll turn it on with the power button, set it to DC voltage, making sure to have the leads in properly seated in COM and voltage. Okay, so if we're using this guy, make sure to use that. For the power supply, there's a switch on the back. Okay, turn that switch on, make sure it's plugged in. And when we turn it on, you can press the middle button there to get on, and it'll have a particular voltage set. It's currently set to 5.1 volts. We'd like it set to 10. So we'll just hit the plus button. Until we get to 10, let it sit, and then we should be good to go. We'll check that voltage on the multimeter, and it reads 10.02 volts. So we'll record that voltage. Okay. So next we need to connect up the power to the potentiometer. So in this, we're going to use some jumper wires and put minus and plus. And then with these leads, trying not to touch them, we're going to clip on the end of that guy, and then we're going to clip this guy on the bottom lug here. It's labeled 1 on this one. Then we have the positive 10 volts here. Going to clip on to that carefully, and then we'll take the positive and we'll put it to the top of the potentiometer. Now we effectively have a voltage divider with 10 volts across the top. We can also we can use this multimeter to measure output voltage, and in this case we'll measure voltage from here to here. Okay, and what's actually a little bit more convenient is on the bottom of this setup, there's some lugs right here. These are actually mini banana, but it works pretty good to just go ahead and put the probes in, and as long as the wires aren't jostled too much, that should give a a decent voltage measurement that's fairly consistent. 7.53. Now, equivalently, for the METEX meter, I use this guy, take this out, positive in the black, the white will do red, and similarly get voltage out of this guy. Okay. So we'll turn that guy off for now, and we'll just use Luke. So the experiment is pretty simple. With the micrometer set to 0, we're going to index that and rotate it around and record different voltages. The instructions tell us what revolutions that we're going to use, how many different measurements that we're going to take. The more, the better and more accurate our sensitivity will be. So as we rotate backwards, one full revolution, you can see the voltage change. And if I'll go out several revolutions, and we can see the voltage beginning to change. It's going down and continuing to go down. So that's the basic for the wiring setup for the experiment. If it's set up like this when you come in the lab, you can use it as is. If you need to do any of that wiring on your own, you can plug that up. It's not too bad to do. So that's the basic setup for the 0 order length transducer calibration. Next, we'll look at a few of the components of this lab. So this is a micrometer spindle head. And you can see that the micrometer has a grade along here, and then a grade all the way around the circumference of the thimble head. As you rotate this, you'll be able to index this in and out, moving the potentiometer in and out. Okay, so you need to look at the numbers here to see what the resolution is. And so if you look closely, you can actually see 0.1 inch, 0.2 inch, 0.3, and in between those there's 4 hash marks. Each of these thimble marks on the outside goes from 0 to all the way around to 25. So 0.025 is what the finest resolution here on this is. Okay, so this thimble head is actually locked up because someone cranked it out all the way out and then really pulled on it, so it's kind of seized, and we'll have to fix that in the shop. So try not to crank these things all the way open beyond their useful range. Another example of one of these micrometer heads, Michitoyo micrometer head here, that is very similar and a little bit more of an accurate one. You'll note that some of these instruments, like I think this one, doesn't have a manufacturer on it. If it does, this one is actually Central Tool, Cranston. Generally, if you don't find the labels on that you're looking for or the resolution, you can just note down that it was not available when you're documenting your equipment. Usually good equipment has good labels on it. On the potentiometer, you can see that there is a label on the side that has the make, model, serial number. It's going to be hard to read in the without the focus here. So you can just trust me here. You're going to need to read that on the side. It also has a little serial number on the side. Now, how does this work? So it's a potentiometer variable resistor. This one is spring loaded, which we've put on here. They don't all have to have springs on them. We have it on there so that it goes back its position. Potentiometers have a specific stroke. You're going to want to account for that anytime you have a potentiometer, and you'll need to figure out what the stroke is on this particular potentiometer. probably familiar with potentiometers in general, from things like your stereo on your car, or your knobs on your vehicle. And so beneath the knob is typically something like looks like this. For a rotary potentiometer, we just turn the knobs, and if we were to be measuring resistance on the back of here, we'd see the same thing, change in resistance along the wiper path. Some rotaries have fancier heads on to keep track of how many rotations we've made, and there's any number of different styles of potentiometers for different purposes. So there's little tiny ones that you typically see on circuit boards, used often for gaining, trimming the gain on amplifiers and things like that in robotic control. So potentiometers are a common electronic component. How do they actually work? So if we were to crack open this potentiometer, we would actually see inside what it looks like. So I'll attempt to sandwich this back together. Here's an example potentiometer that is similar to that. It's got a rod that goes in and out. And we can crack open the case and take a look at it. So we can see wiper goes like up and down like this. And on one side of it, you can see that the side that has the shaft connected to it, there's actually just an electrical contact wiper that's kind of like spring-loaded here, okay? And then on this side, you see little electrical bars that are conductive. And the nice thing about them is they're fabricated so that as the wiper goes up and down contacting that bar, you can actually get a variable resistance that's pretty precise. So for example, if we take our multimeter, set it up for ohms, let's see here. And then we start to wipe up and down that conductive path, you can see how the resistance changes. And that's the basics of a potentiometer. So you can imagine that this can be very useful. One of the design constraints that you have with a potentiometer is wear. And so these contact points can wear out, and these bars can wear out with too much travel, and they're also susceptible to mechanical noise as you're moving up and down. Also, if you're moving up and down too fast, you can generate heat by this friction contact, and that's another element of error with a linear transducer that's a potentiometer basis. There's other kinds of position sensors, and one example that is probably most common in mechanical engineering is an LVDT, okay? And so I'll actually pull up the course page referencing this first. So you can see under chapter 12, under displacement sensors, you can see the basics of an LVDT. It's got a solid core. So take the core out, and it's just a steel rod, iron rod that goes inside. And there's a coil of wire. It's called a primary coil. That AC voltage is supplied typically at a high frequency. And then there's two secondary coils that are on the outside of the primary coil. Those secondary coils pick up voltage inductively from the primary coil, but the amount of voltage that are picked up on the secondary coils changes with the core position. So as the core moves up and down, more or less voltage is evident on the output. And so we can use an RMS multimeter to read the output and calibrate that to position. The nice thing about this is even though there's a little bit of contact, it's not much. And these LVDTs can be quite accurate, quite a bit more accurate than the potentiometers. And they also are less susceptible to friction and wear. So those are the basics of some position measurements that we might use for depth studies. So going back to the assignment, make sure that you note test objective and ambient conditions, temperature, pressure. Make a list of test equipment with as many details as you can get on it. Measure total resistance of the potentiometer. Set the power supply to 10 and measure that voltage. Wire the potentiometer up. Set the micrometer position to 0, and then index the micrometer measuring voltage in 0.05-inch increments from 0 to 1 inch, and tabulate that. Eventually, you're going to then plot that with a linked versus voltage plot, adding a trend line, tidal axis, and units. And then you can use regression. You can take it in take the data into Excel if you'd like, to figure out what the slope of the line is. You can also do it graphically if you wished, using the linest function if you're in Excel. You'll be able to get the slope or sensitivity K from that, and you'll also try to tabulate the appropriate errors using equation 1.1 and note the maximum error. Just like other instruments, you'll want to establish a specifications table, including the range, excitation voltage, output range, sensitivity, linearity error from at full scale output. Try to make a comment of the accuracy of the link transducer. These are pretty good instruments, so we expect them to be very linear, and also give an estimate of the current and power used in this potentiometer. Finally, always make a comment on any known or suspected sources of error during the experiment. So that should be it for the zero order linked transducer static sensitivity test.